we discuss about the retrosynthesis, where looks like the difficult one since the organic synthesis has emerged as a very good tool for the synthesis of various kinds of drug molecules. Since everyone knows that during the not only in the pandemic but during the several years, even in the decades, we know that there are several diseases appeared since from the 100 year and in the previous years also, previous years. So what happens is that later on in after the 19th century, the concept arises that these chemical compounds can be used as a drug molecules. So in the classical history or in the traditional history, there are several Ayurvedic examples are there. Maharishi Kanad and also the later on Sant Mahapurush. They also used to use the technique where they use the plants to crush it and mix it with wet, and then they give the extract to the diseases oriented people, and it gets cured. So nowadays, that concept is already continues in the today's era also. But the thing is that while they mix it with each other, what is happening at the molecular level? So they don't understand that one. But the result ultimately it was good always. So that at the molecular level, there might be a mixing of two plant material and three plant material together. They crush it or they heat it. So during that mixture, what is happening is that at the molecular level, some of the drugs molecules which are present in the plants get activated by heating of that mixture, and that the whole portion is given to the disease-oriented people, and then disease gets cured. So this is the broad concept. It was in the previous era also and current era. So the thing is that based on the synthesis of various drug molecules, this field it looks like difficult for those who don't understand the complete reactions, and that's what many scientists usually not prefers to go for the synthetic pathways in order to synthesize the drugs. So less people are oriented, less research people are oriented towards the synthesis of various drug molecules. But the concept is that how we can make it. You see, we do have several diseases. We do have the so many and cancer types diseases. We have the leprosy, we have the AIDS, we have so many. So what kind of there are still in the current era there is no final solution is appeared for all the diseases. Even though millions of scientists, millions of students are working on the scientific field where they are trying to develop the concepts, new concepts, so that the diseases can be cured. But it nobody gets 100% surety. So the thing is that from chemistry point of view, organic synthesis it was emerged as a amazing, excellent tool in order to synthesize the compound. Suppose we are having a compound which is present in the sea. So depth of the sea, so there will be some plants, and that plant contains specific kinds of natural products, and that has been confirmed from the spectroscopic technique that this is the target molecule, and that has a very unique character. It can be used to cure various diseases. But the thing is that the availability of that plant is rare, very rare. So you cannot get too much amount of the plant material and get isolated from the compound can be isolated. It will be very very less. It will be in milligram scale also. So it's not possible to get in the bulk amount. So the concept arises is that rather than isolate the components which is available in the plant material, why not try to synthesize it in the chemical laboratories? And that is what the chemical synthesis emerged as a excellent tool for the synthesis of those compounds which are not commercially available and which are very rare. And that's what the disconnection approach later on was being developed by the E.J. Corey, and in the synthesis of the new synthesis of new drug molecules, it is based on the retrosynthesis. So retrosynthesis is nothing but the disconnection of the target molecule into the smaller units, so that we can use the knowledge which do we have the reliable knowledge to apply it and make the synthesis happen. So this is what the concept arises in the retrosynthesis analysis. So the portion it has given in the syllabus is the disconnection approach, one group CC disconnections and two group CC disconnections. So all the portions included here, I have tried to make the reliable slide, which is taken from the net also. So if we start with the history of synthesis, what happens so that there's a birth of total synthesis. So total synthesis is a concept where the target molecule is being synthesized fully. So that's what we call it as photosynthesis. Sometimes the target molecule may be disconnected into the two smaller units. So if we synthesize only one of this one, we call it as facile synthesis. So this is also another concept where facile synthesis takes place, or intermediate synthesis. We call intermediate synthesis, but the total synthesis is related with the target molecule synthesis, where there will be no further reaction. So once the target molecule is achieved, you don't have to go for the further reaction. You can directly use it in the clinical trials, and that is what the concept of total synthesis arises here. So it was around 19th century the concept was arises, and everybody knows that the Wohler, who was the first scientist who prepared the urea in the 1828. You can see the year; it was very old concept, and that was the first component in the organic compound or in the chemistry itself. I think it was the first one. It was get synthesized. And after almost like you see, almost like 50, 60 years later, Kolbe was a scientist. He coined the word synthesis, and that's after the word was coined by the Kolbe, and everybody trying to explain the concept related to the chemical reactions for the synthesis of target molecules. Synthesis word was emerged. One of the most important things in the 19th century was the synthesis of glucose. Usually glucose is being synthesized from the plant materials via the porphyrin rings. So in this case, the glucose moiety is chemically synthesized in the 19th century. So that is what the people come to know that yes, there are this is the outstanding chemistry can be arises from the carbon compound. And carbon compound, why carbon compound? Because of the driving force of the carbon compound is that the capability of the carbon compound to get coupled with the another carbon, and the CC bond formation or CC hetero bond formation takes place, and through the way where we can generate millions of compounds. Today, if you look at the today's situation, every day new 70,000 new compounds from all over the world. We are looking at very few examples, but in the world 70,000 new compound is newly added every day. So one day we are having 70,000 compounds. That means the capacity of carbon, that is what we call catenation power, which is being studied from the 11th standard. So that catenation power which is found in the carbon is very unique, and that's why because of based on that one, the organic chemistry was being the frontier field, where it is being now dominated all over the pharmaceutical industries. If you take the current example where we are getting the vaccine for the COVID-19, so in that also it plays a very key role, because the pharmaceutical industry in India are very big. They are having capacity to synthesize almost like 10 ton, 20 ton or 100 ton in 1 week. They can synthesize one molecule if it is desired. Even though it is 5 steps or 6 steps, they can prepare 100 ton. I am not talking about milligram. I am talking about 100 ton or more in even in the pure quantity. So that much big plants are available in the India, and that's why India is almost I think maybe more than 60% of the world pharmaceutical drugs has been synthesized in India, and they are exporting to the whole world. So this is what we have the very excellent capacity, and through the organic chemistry only we can understand how we can synthesize the molecules, and this is very unique thing. So this was the urea. As everybody knows, the urea contains the carbonyl group and the two amino groups. So this was the first synthesis, and Kolbe later on he synthesized the acetic acid. And Fischer, this was the very excellent discovery, and Fischer in 1890, you see, it was almost like 120 years back. He synthesized with the glucose, and after the synthesis of, we are looking at the history just only. So the simple targets used to synthesize in the previous years, but nowadays the compound become complex. So it is really difficult and imperial when the target becomes complex. So it will be difficult to synthesize those molecules. So the concept is the synthesis of any kind of molecule. We should use the reliable chemistry which we learn from the textbook. We cannot design a molecule without the knowledge of having the similar reactions has been used in the previous phases. So this is what the intellectual planning comes there. And the skills are very required important, because without having a skill to operate the reactions, you cannot synthesize the difficult targets. That's why the skills is very important in order to synthesize the compounds. Intellectual planning comes where we are very high level. You see, this word is important, because commonly when you are going to synthesize any kind of compound, you are going to break it, and after the breaking, something like building material, we have to make the columns, we have to make the or the stepwise bricks has to be added, and then later on we have to put the slab, and there are many things. So it has to come from the basic to the higher, and the building will be formed. The same concept is applied here. In order to form a target molecule, you have to make into the smaller pieces, and that pieces of knowledge has to be come from the knowledge which is available in the history, reliable knowledge. जो भी रिएक्शंस अभी तक डेवलप हुए हैं, उसी को पकड़ के हमको वो टारगेट बनाना है. वी कैनॉट डिजाइन अ मॉलिक्यूल विच वी डोंट हैव एनी काइंड ऑफ रिएक्शन समथिंग लाइक दैट वन. And that's what the main problem comes here. You should be at least intellectual enough in order to plan this kind of synthesis. तो उससे क्या होता है कि एक अंडरस्टैंडिंग भी जो रहता है रिएक्शन मैकेनिज्म का, तो वो भी बहुत अच्छी तरह से समझ में आ जाता है, और नॉलेज भी रहता है वो रिलायबल रिएक्शन. दिस इज नॉट इम्पॉर्टेंट. Without having the concerted reaction or the concerned reaction which is being already developed, that can be used for the synthesis purpose. Or there are several conformations, there are several stereochemistry related compounds are available in the nature. As everybody knows, we have the R compound, we have the S compound, we have the distereomer, we have several complex molecules where we have more number of stereo centers also there. So it is very difficult to synthesize those molecules, and the proper understanding should be there. Without the understanding of which kind of stereo center is generated, we cannot go ahead, and that's what we must have a very depth knowledge of the synthesis. Second is that we have now in the previous era, they don't have any NMR, they don't have any mass, they don't have even IR, but still that those people, they were able to synthesize these molecules. You see how much intellectual they were, based on the very basic kinds of reaction, something we learned in the laboratory, acid base reactions, and we check the pH, and we try to check the functional group test, and based on that one, they were able to develop this kind of chemistry. But nowadays everything is there. We have the IR, we have mass, we have HPLC, we have retro, we have the high frequency NMR 500, 600. Nowadays 900 megahertz NMR is also appeared, 1200 megahertz NMR. So that kind of NMR not only confirms the carbon compounds, they will also make sure the phosphorus, they will also check in the nitrogen, and they also are checking the chlorine or the halo compounds. So it is very important that the spectroscopic techniques and the methods which do we have currently, it is very easy to locate the some synthetic compounds. So spectroscopic technique is something like an eye. If we look at the human body, if we don't have eyes, so we cannot see anything. So if once we prepare any kind of compound or any intermediate, we can check this through the eyes of spectroscopic technique. Through this one, we can make sure how many carbons are there, how many hydrogens are there, what is the molecular weight, how many stretching bonds are there, vibrating bonds are there, how many acid peak will appear or not. There are so many concepts. Whether the interaction in between the 1 to 3 carbon atom, no C will be there, HPLC, HSQC, HMBC, there are several interactions. We can also make sure in the 2D NMR. So these are the concepts where these are the spectroscopic techniques which we can utilize it in order to synthesize the molecule. That's what the history of synthesis appears to be very predominant over the other chemistry. So in retrosynthesis, there are two ways to synthesize the compounds. First is that linear synthesis. So linear synthesis is nothing but we have to take one component in the beginning and continuously with that component only we do the several reactions. And after doing the several reactions, it may be 5 steps, it may be 10 steps, it may be 24 steps, it may be 30 or 50 steps also. So once we take the starting material, it will go to direct to the target molecule. And this is what the linear synthesis comes, where we don't have to break the chain in between. You will get, once you prepare the second compound, that can be used for the third can be used for the fourth. So this will get continue until we reach to the target molecule. And this was about the overall yield. The yield, once we know for each step, it can be used to calculate the overall yield. So it is very easy. If we have the one step 0.80, it is now commonly taken. So 0.80, 0.80, 0.80. So if we consider for the three steps, so this into this 0.8, 0.8, usually 80% we have to take it as a 0.8. So this is the way where how we can check the overall yield. So 0.8, 0.8 and 0.8. So it is 10 to the 0.80, 10 to the power 3 will come. So if you calculate from the calculator also it will appear. And this if you take the conversion, how it will be around 51, 0.51. So and this 0.51 into 100 it will be like 51%. So this is very good overall yield. But once the steps is increases, the yield will get drops. So this is the main thing where we can found in the chemical synthesis. Once you are increasing the steps, number of steps starting from the first one to the last one, if we increase it, the yield will get dropped, because every time once we calculate it, every time it will get in dropping. So if we calculate with these two, it will be around 75%. Once we go into third step, it will again 25% decrease. So once we are decreasing, we are increasing the steps, the overall yield will be in decreasing order. So this is the order which we have in the organic synthesis. So this is the example they have given for the linear synthesis. Paracetamol, as everyone knows, that this is a kind of drug used to treat the fever. So commonly it is very common drug, and very cheap also. So how it is prepared? So the step which is being used for the synthesis, they did not give the retrosynthesis right now. Just try to understand what kind of synthesis can be. There are several versions. So first is that phenol. Phenol is used to treat with the nitric acid. So we get the para nitrophenol. So this is the first case. So since we have the electron donating group, so usually electron donating group will be preferred as to have the orthopara directions. If we have a electron withdrawing group, then it is usually the meta directing group will be there. So what will be there? So here orthopara directing means what? The para position here we are occupying by the incoming nucleophile, we get the major compound. So this is the first one. And second step is that we are reducing it. So reduction takes place, we get the amine. And in the third step, acetylation. So the final target molecule contains the acetyl group, NH group, and phenolic group. And this one will get the final compound. Next linear synthesis is that musk ambrate perfume. This is a kind of perfume, and this is the structure. And you see the tertiary butyl group is there, methoxy group is there, nitro group is there, two nitro groups is there, and methyl group. So that means one electron donating group, second electron donating group, third electron donating group. So we have the three electron donating groups, and two, this one and this one, electron withdrawing group. So two electron withdrawing groups. So how to deal with this one? Since we are having the orientation pattern, how we can synthesize the compound in aromatic system by using the chemistry where we have the orthopara direction with respect to the electron donating, and withdrawing group we have the meta direction. So the for this synthesis, this was the plausible starting material. So M-cresol, where we have the hydroxyl group there. So and it is at the same position. You see the concept is that the methyl group is already there, benzene is there, and OH. So it is being cleaved from this side. So this OH can be converted into the OMe. Very simple, methyl sulfate is the one option, or we can also use the methyl iodide with triethylamine. So this is the another one where we can use the alternative method. So under basic conditions both, so it will come the methylation. So one target is completed. Second is that once we have this one donating group, and this is also donating group, so it is orthopara direction. So usually this position is now being occupied by the incoming nucleophile. And everybody knows that by using the anhydrous AlCH, something like Friedel-Crafts reaction also, Lewis acidic condition, we can synthesize this kind of molecule. They did not give the side product, it must be appeared something at this side, but this may be the major one. So the major component only they have kept. And lastly, once we have all the donating group, so the meta-directing group usually is directly used the nitration. So the nitration will be takes place this side and this side. So it will form the final molecule. So there will be some tricky questions will be appeared, but we are not going to look at that. Just try to understand the linear synthesis right now. Later on we will see everything. So second concept is that convergence synthesis. So in convergence synthesis, what happens is that they will synthesize the one target molecule and second target molecule through the two different pathways, and it will merge in one step to get the final molecule, and this is what we call the convergence synthesis. So in convergence synthesis, two different pathways is being followed from the two different starting materials in order to reach to one stage where this kind of one starting material and this kind of other starting material can be used to mix with each other with the functional group so that we can get the target molecule. And this is what the concept is arise. But this the yield is, you see the yield for the linear synthesis, it was very less, since every step it will get decreases. But in convergence synthesis, what happens, after the three steps we get the molecule, after the three steps we get the molecule, and we are just mixing these two, and based on this one the yield is very high now, because if we keep these three steps continuously, what will happen, it will get decreased continuously. So the flow of overall yield is being broken here, so that the first step and the second step synthesis can be done by the coupling in the later stage. And that is what now it is considered that this is 1, this is 2, this is 3, and this is 4. So it becomes actually ultimately actually it is how many steps, 3 and 3 6 and 7 steps. So before also it was like 1 2 3 4 5 6 steps, so 6 steps 21%. But now even though it is 7 steps, but the way of treatment is different. So this 3 and this 3 is now counted as only 3, since we are using the one target molecule from this side and other target molecule from this side, and we are just coupling it. So what happens here, the 3 plus 1, so it will be around 4 steps. So that means it is now considered as the highest overall rate. So usually people don't prefer to go for the linear synthesis, they try to synthesize in the convergent manner, so that they can break the different moieties, and they synthesize the two different target molecules, and just later on they can couple it. And here is the example how we can do the convergent synthesis. So in convergent synthesis, if you look at the first step, you see now this is the target molecule. So Benadryl is the drug which is now being synthesized. So in this drug, first we have to see how many kinds of bonds can be prepared or can be synthesized. So here is the concept where CO bond can be broken. Next is that we can also prepare the CN bond here. CO bond broken and CO, and this is the intermediate where we have the two CH2 groups, and this can be comes from the epoxide. So everybody knows that epoxide is a very good source of having the two methylene groups, and here we have the two methylene groups. So why not use the epoxide? Yes, of course it can be. And the nucleophilic addition from the amine, so this is the another one. So dimethylamine is also commercially available. So very simple concept arises here. The lone pair of electrons go to attack at the any carbon side, and the ring will get open. And once the ring get open, later on this proton is now gets shifted towards the alkoxide, and we get the stabilized moiety. And this is what the first moiety appeared from the target molecule. Second is that we have to synthesize this kind of moiety. So for the second step, what they have done, they have chosen a moiety where they can break from this side. Why this side? Because we have the primary alcohol. So the next reaction can be from the primary alcohol. That's why we can break from here. So the concept arises that we should have a compound which contains the halide group here, because from one side we have the alcohol, so it can be used as a nucleophile. So the electrophilic center containing compound should be there, and we know that electrophilic center can be appeared by the addition of halo group there. If there is no halo group, this carbon is now neutral, right? So once we put the halo group there, and there is a very good reagent where we can use the benzyl site, which can be brominated, specifically the isolated carbon atom. If you take toluene also, it will work, it will be brominated, but this is the commercially available compound where we can use the first bromination. So the second target molecule is ready. So the first one and second one now we have the electrophilic center here, and we have the nucleophilic center here. So nucleophile is there. So that can be coupled together in order to form the CO bond. The bromine get departed and we can generate the target molecule. And this is what the way where we can do the converter synthesis. So if you look at the comparison in between the linear versus the converger synthesis, which is good one? Actually, both is good one only, but with respect to the yield, because from this way also we are generating the natural product or the target molecule, and this way also we are generating the target molecule. So the importance of target molecule is really very important. Otherwise, if we do not synthesize these compounds, we cannot get any pharmaceutical drugs in the pharmacy. And that's what both the synthesis is of course very important, but with respect to the yield, this is good one. So that's the reason people usually prefer to synthesize the target molecule by making the small component, and then later on they couple it to get the final one. So this was about the types of synthesis. Later on, now we are going to exactly now we start our study. So retrosynthesis analysis. So retrosynthesis, this is the arrow where the double-headed arrow is given there, and this whenever you see this kind of arrow, that means this is retrosynthesis. So retrosynthesis is nothing but the disconnection of the target molecule into the smaller units and via imaginary concept, and that's what we call it as this target molecule could be synthesized from these smaller units, and this is what the retrosynthesis arises. And E.J. Corey, one of the best scientists in organic chemistry in the Harvard University, you can see he, I think, have almost created more than 100 PhDs. If you look at to the website, and he have more than 50 postdocs. So you can understand how much brilliant he was. In the young stage when he started his career, he was very keen. If you look at the history of E.J. Corey, he was very keen researcher, and I think more than 1000 or 2000 natural products, the target molecule, which is very complex also, he was synthesized in his laboratory, and that's why he later on found that the scheme, what we call nowadays retrosynthesis analysis, and he was the pioneer of the concept. He was the one who developed this kind of concept. And thus is the concept for the retrosynthesis analysis is based entirely on the transformation of organic reactors. Without having the transformation, we cannot get any kind of retrosynthetic compounds. So in open arrow, this is the open arrow, retrosynthetic arrow we can call it as a, and it is used to transform withdrawn from the target to the precursor. Now you see, every reaction we studied so far is always from the target molecule is synthesized from the smaller units, but we start from the units and we get the compounds. Now what happens in the retrosynthesis, we are keeping this as a target and this is as the precursors. So you see, this is the precursors now. So the left hand side which we seen here, this is gone in the right hand side, and this comes in the reverse side. So that's what retrosynthesis comes, where the target molecule is the first written, and that can be prepared, that can be, that could be, that might be, that maybe. These are the ways how we can explain the retrosynthesis. You cannot say this is prepared from this one. You have to say always that the target molecule A can be prepared from B. It is not the sure one, we are just designing it, and that's what retrosynthesis comes. So in order to design, we must have to know several concepts. So for the disconnection approach, now you see disconnection. So this is the target molecule which was being in the always in the right hand side during our reactions, always in the right side. But now reverse concept is appeared, that the target molecule will be comes in the beginning. And now rather than doing the reaction of this one, you have to break it. in such a way that we can make the commercially available precursors, and this is also we call synthons. The positively charged or the negatively charged components which is generated from the target molecule through the imaginary way via retrosynthesis analysis, and that's what we are disconnecting the molecule, we are breaking the molecules, and we are cleaving the molecules. So through this one we can know whether the molecule can be generated or not, and that's what the disconnection is appeared, the concept of disconnection. Usually in the regular synthesis for everywhere, we are connecting the molecules every time and we get the final one. But now final one comes first through the disconnection via the breaking of bonds and cleavage of bonds. And this is the concept where we can synthesize this kind of moiety from the precursors, synthons. And synthons always, as everybody knows that for the reaction, for the organic chemistry reaction, we should have a carbanion or we should have a electrophile or nucleophile. Simply we can say, rather than intermediate, we can say we should have one electrophilic center and we should have the one nucleophilic center. And this is what the concept is arises. The first way of generation of this one is to, of course, we can break this bond. Why? Because we know that the aromatic ring can be used to get acylated to the Friedel-Crafts reaction. तो आपको अगर Friedel-Crafts reaction पता है और आपको यह इस molecule को बनाना है, if you don't know the Friedel-Crafts, you cannot synthesize it, and that is what the intellectual is appeared here. So whatever the knowledge we received so far in the organic chemistry, as in the form of name reactors or in the form of various other concepts, that is now used to apply for the making of molecules, and this is what the intellectual skills is appeared. If you don't know the basic chemistry, if you don't know the exact reaction, what that reaction will do, then only you are able to synthesize the target molecule. Now this is the one where this is a very simple component where we have seen the aromatic ring is there, methoxy group is also there, and we have the acyl group. So the concept will immediately comes in your mind. The acyl group is there, means acyl group can be inserted onto the aromatic ring via which kind of reactions. So this was the first question which should arise in your mind. And once you know the breaking of which portion, we get the which components. So once you understand the acyl group can be inserted, you must have to remember the Friedel-Crafts reaction. If you don't remember the Friedel-Crafts, then it's not easy for you to go for the disconnections. And this is what the concept of retrosynthesis or disconnection approach looks difficult. You see the target molecule transformed from the synthons which is appeared by the equivalent or reagents. So those reagents which is being already developed by the scientific community. Of course, that concept can be directly used for the target molecule synthesis, and this is what this is not that much difficult. But as a student, it might face you might feels that this is looks difficult. But actually, this is very simple. If you understand the concept, if you know the reaction, and if you understand that how we can break it, it is very simple. You can synthesize any molecules. Once you go through the process, that is what the PhD is really important in this case. Because if you are working on the not only any carbohydrate chemistry or synthetic chemistry, where you are preparing a target molecule, you will understand how many problems you will face in order to synthesize it. Because this looks like imaginary ways to the imaginary way, this looks like simple. But when you are applying your knowledge for the synthesis of the respective compounds, what will happen? Theoretically, we know that this could be a reaction. But when you go practically, because there are two aspects. One is that theoretical concepts, other is that practical concept. So theoretical chemistry applied for the practical one, and practical chemistry when you are practically treating the components with the reagent, and sometimes what happens, what the concept which we have arises via the common chemistry, that will get failed, because sometimes the component which we are treating practically, that might have the different properties, because every component, if we change the here oxygen to sulfur, the properties of whole molecule get different, and that's what it feels more difficult, that every step you might be not sure whether the compound is generated, and if it is generated it can be confirmed via the spectroscopic analysis. And this is what the tricky part is appeared in the synthesis, that in order to synthesize any kind of components or compounds, you must have to go through the several difficulties. Now I will not discuss there are so many issues are there, so many things are there, I don't want to explain it here, but just try to understand it's not easy to disconnect it, and that's why the disconnection approach which is given by EJ Core, it looks more concise when you understand it, but it looks difficult when you get confused. So here also you see, after the breaking of this one, let me change the color. After this breaking, what happens, we can generate the carbanion one way, and once you generate the negative charge from one unit, alternative unit should be positive. This is very common. This is the pathway A. In pathway B, what happens, we have, if we consider this is, we are having the positive charge and the alternative should be negative one. So this is just the imaginary bond breaking. Next, practically see how it can be done. This is the same target molecule, synthons. Synthons is the imaginary components where we can write it down through the imagination, where there is a possible size in order to get the exact charges. So now if we keep the negative charge here, so what we have to you try, so here there might be a possibility of having the hydrogen. Is there this kind of compound is commercially available? Yes. Anisole, this is what we call anisole. Methoxy group is there, anisole is available commercially. So the concept is that those molecules which we are breaking, it should be commercially available. We cannot choose a target or component which is not available. Otherwise, what we have to do, we have to synthesize it through the different ways. Synthesis in the different ways, and then we can utilize for the reaction. So there is another concept in the synthesis, that if you don't have the commercially available unit, then you have to synthesize from again smaller units. This becomes more complex again. So this one, of course, positive charge can be applied by the halo atom. So acetyl chloride, yes, of course, this is also commercially available. So this is, we knows that once we understand why the breaking of CC bond, we can generate this kind of moiety, and the moiety or the synthons is plausible to have the similar functional groups with respect to their availability in the commercial purpose. Now next step is that through the imagination, through the disconnection, we understand there may be a possibility of addition of acetyl chloride and starting material. Here the concept is arises real craft. So by using AlCl3, anhydrous AlCl3, we can use the anisole to get the para position, और उसमें भी हमको ये देखना पड़ेगा कि फिडल क्राफ्ट में ऑर्थो पैरा डायरेक्शन मैटर करता है या मेटा डायरेक्शन मैटर करता है, या इलेक्ट्रॉन डोनेटिंग ग्रुप है तो कहाँ से जाएगा तो परफेक्टली बनेगा कि नहीं, ये सब चीज़ें आपको रिएक्शन में मिल जाएगी जो ऑलरेडी डेवलप हुई है. Those concepts which we are now discussing is that already developed chemistry is now utilized for the synthesis of target molecule. So this is very simple concept. So anhydrous AlCl3 use करने के बाद we know that the acyl group can be inserted at the para position. Yes. So in one step we can get the target molecule. So this looks like very simple synthesis. Next, if we go for the paracetamol alternative synthesis, what can be the possibility? Here is the disconnection retrosynthesis analysis approach. We can also say approach. So once we know the target molecule structure, so we should have to understand what kind of functional group are present there. So this is the first one. Once you see the target molecule, what we have to do, first check the functional groups. Then after checking the functional groups, try to cleave the functional group in such a way that we can get the new bond where that bond is possible to make via the reliable chemistry which is already we learned. So in this one, this is the amide bond, and amide bond can be prepared from the NH2 R plus acid, right? एसिड से भी बना सकते हो, तो ये एसिड से कैसे बनेगा? अगर एसिड के साथ अमीन का रिएक्शन करोगे तो भी बनता है, अगर उसके साथ नहीं हो रहा है तो एसिड क्लोराइड भी यूज करते हैं। तो दिस इज ऑलरेडी वेल नोन रिएक्शन। ये रिएक्शन हमको पहले ही पता थी, लेकिन ये अप्लाई कहाँ पे हुई है? यहाँ पे हुई है, फॉर द synthesis of amide bond, and that's why the first disconnection appeared here. So NH will minus will appear and this plus will appear. So NH minus, and one side it is minus, other side it is plus, and this can be this is the synthon can be generated from the acetyl chloride. एंड नाउ अगेन एसिटिल क्लोराइड अगर आपके पास नहीं है, तो अगर आपको उसको भी बनाना है, लैब में अवेलेबल नहीं है, आपने ऑर्डर किया है और उसको आने को 15 दिन है और आपको कंपाउंड को फिनिश करना है, तो व्हाट यू विल डू? यू विल अगेन सी द कंपोनेंट विच वी आर यूजिंग वेदर इट हैज अ पॉसिबिलिटी टू जनरेट फ्रॉम एनी अदर मॉलिक्यूल। यस, ऑफ कोर्स, वाया दी क्लोरीनेशन। तो एसिटिक एसिड का अगर हम क्लोरीनेशन करते हैं अल्कोहलिक पोजीशन के ऊपर, इस पोजीशन के ऊपर, so it will form this molecule. Yes, this is also reliable chemistry, and that's why the retrosynthesis and analysis of paracetamol looks like from the one way we can have the synthetic pathway. So now this is, of course, we understand that we can have the NH. लेकिन if we don't have this kind of moiety also is not commercially available. ये भी अभी commercially available नहीं है, तो क्या करोगे? तो फिर आपको इसको भी ब्रेक करना पड़ेगा, और इसको ब्रेक करना है तो आपको सोचना पड़ेगा कि NH2 वाला जो ये कंपोनेंट है ये कैसे बन सकता है। तो ऐसे कौन सी केमिस्ट्री है जो NH2 ग्रुप अपीयर हो सकता है इसके ऊपर? यस, ऑफ कोर्स वी नो दैट NO2 कैन बी चेंज टू रिड्यूस टू NH2। तो ये पॉसिबल पाते हैं, इसलिए फंक्शनल ग्रुप इंटर कन्वर्सन आया यहाँ पे। उसके बाद ये भी पता लगाना होगा कि अगर NO2 ग्रुप एरोमेटिक रिंग के ऊपर पैरा पोजिशन पे OH है तो आता है क्या, तो वो भी देखना पड़ेगा। नाइट्रेशन, यस, नाइट्रेशन रिएक्शन भी हम करते हैं। जब इलेक्ट्रॉन डोनेटिंग ग्रुप रहता है तो यूजुअली डोनेटिंग ग्रुप के लिए ऑर्थोपैरा डायरेक्शन कंपाउंड मिलता है। यस, द केमिस्ट्री विच वी हैव ऑलरेडी इन द केमिस्ट्री बुक्स इज नाउ अप्लाइंग। So the nitro group can be inserted via orthopara direction. Of course, we can get the meta position also, but that compound may be the minor one. So just try to get the major one. And this can be also prepared from the negative charge, or that can be having the hydrogen atom. So the negative charge is there means we have a component where we have the hydroxyl group there. Yes, phenol, which is very well known solvent also, and also organic compound which is also commercially available. Whether we have the nitration जो हम कर रहे हैं, नाइट्रेशन के लिए कुछ रिएजेंट यूज होता है, whether we do have that one, yes, also acid nitric acid is used as a nitration purpose via the mechanism where nitric acid and H2SO were used. तो देखो ये डिस्कनेक्शन कैसे होते जाता है। जैसे टारगेट मॉलिक्यूल है उसको ब्रेक करते करते हम इस स्टेज पे जाते हैं कि जहाँ पे आपको स्टार्टिंग मटेरियल का टारगेट मिल जाता है, यूनिट मिल जाता है, वेयर यू कैन स्टार्ट द सिंथेसिस, एंड दिस इज व्हाट वी कॉल रिट्रोसिंथेसिस एनालिसिस। नेक्स्ट, अब क्या करो, जो फर्स्ट स्टेप था हमारा ये वाला, फर्स्ट स्टेप इन रिट्रोसिंथेसिस विल बिकम द लास्ट स्टेप, क्योंकि लास्ट में हमको ये बनाना था, बन जाएगा ये। और जो लास्ट स्टेप था यहाँ पे, ये जो लास्ट स्टेप थे वो फर्स्ट स्टेप बनेंगे। व्हाई? बिकॉज वी आर स्टार्टिंग फ्रॉम दिस यूनिट्स, वी आर स्टार्टिंग द केमिकल सिंथेसिस इन रिवर्स मैनर, एंड दैट्स व्हाट वी कॉल इट एज रिट्रो एनालिसिस। तो यहाँ पे देखो लास्ट वाला कौन सा था? फिनॉल था। तो द सिंथेसिस विल स्टार्ट फ्रॉम द लास्ट। तो फिनॉल का नाइट्रेशन किया, ऑफ कोर्स नाइट्रेशन के बाद NO2 ग्रुप आ गया। अब ये भी पता है कि नाइट्रेशन को हमको क्या करना था, नेक्स्ट स्टेप में अमीन कन्वर्ट करना था। यस, तो सेकंड स्टेप विल बी रिडक्शन। और जैसे रिडक्शन बनता है, हमको ये भी पता है कि NH2 एंड एसिड क्लोराइड का रिएक्शन अनहाइड्रस AlCl3 के साथ करेंगे तो N असाइलेशन होता है। देखो आपने असाइलेशन बहुत बार किया होगा, है ना। जैसे OH का भी कन्वर्शन हम OAC में कर सकते हैं। देयर आर सेवरल रिएजेंट, वी कैन यूज एसिटिक हाइड्राइड, वी कैन ऑल्सो यूज अल्टरनेटिवली एसिटिल क्लोराइड ऑल्सो इफ यू डोंट हैव दिस वन। सो व्हाट वी कैन डू, simply by the acylation reaction. Yes, in the final stage, first step is that नाइट्रेशन, एक स्टेप हो गया। देन सेकंड स्टेप इज दैट रिडक्शन, अमीन बन गया। एंड थर्ड स्टेप में वी आर जस्ट पुटिंग द असाइल ग्रुप। लुक्स लाइक 3 steps, but for this 3 steps, how much it has to go with the related reliable chemistry? This looks difficult in the retrosynthesis. Actually, this is the well-known synthesis, but in our laboratory, one of the students in the previous year batch, Rajesh Belgamwar, I give him the target of paracetamol synthesis, this one. So what we think, you see, there are at least 3 to 4 steps, or some steps is there where we can synthesize the paracetamol in various steps. So here you see, one step is nitration, then second step, and this is third step. This is the same molecule which we are looking at now. The 3 steps are there. So what I thought, rather than having the 3 step synthesis, we can make it in one step. This is what we call one pot synthesis. And yes, it was confirms that it has the condition. I did not give it here. We have the reason which is not being published so far. So I will publish later on. So the thing is that what I have given him, rather than giving this kind of moiety, because we wanted to insert the NH2 there. So rather than inserting to the 2 steps, you see 2 steps they have taken in order to insert the NH2. So what I thought, why not use the chemistry where we can use the halide atom, and so once we use the halide here, so this carbon becomes positive, and now we give the ammonia here. This is negative now. So the concept which we are looking at, practically I have already applied in the synthesis of paracetamol. So the negative portion of course can be used to couple with this one, and we tried several reactions with different solvents also. And lastly, yes, he got the compound where the NH2 is inserted there वाया द बेंजाइन मैकेनिज्म. अगर आप बर्च रिडक्शन भी देखते हो ना, उसके साथ एक बेंजाइन मैकेनिज्म भी आता है. So where we can see the ammonia can be used as a nucleophile rather than you precursor nitrate NO2 used there in 2 steps. Why not use the related component where we can use the directly insertion. तो एक स्टेप हो गया. सर दूसरा स्टेप तो ये तो पता ही है हमको, जैसे यहाँ पे NH2 आता है तो वी कैन इंसर्ट दी एसाइलेशन. तो एक्चुअल में वो डेवलप किया था हमने 2 स्टेप में. तो बाद में हमने क्या किया कि जैसे ये फर्स्ट स्टेप कंप्लीट हुआ, NH2 बन गया, उसी रिएक्शन क्लास में जैसे एक क्लास लिया है हमने, और उस क्लास में हमने क्या किया है, पैराबोरोमोफिनॉल ये कंपोनेंट डाल दिया, फिर अमोनिया भी डाला है उसी में, उसमें भी सॉल्वेंट भी है, and we stirred the reaction for I think 110 degrees Celsius, something like in different solvents. So what happens, we get the target molecule via TLC. So what I told him, rather than isolate this kind of component, because every step we have to isolate it, purify it and go for the next step. So what I told him, rather than isolation, because it was the basic condition, and this reaction is also under basic condition. You see, they have used here acidic condition, of course. But for my case, what I thought, after the generation of this one, use the basic condition, because once we have the NH2, this is a labile proton. And this is a basic, under basic condition, there is a possibility of removal of this proton also. तो यहाँ पे 2 प्रॉब्लम क्या आए थे हमको, कि जैसे हम ट्राई कर रहे थे कि बेसिक कंडीशन में NH का ही असाइलेशन होना चाहिए, नॉट दिस वन, क्योंकि वी हैव द phenolic OH, and phenolic OH is acidic also. And if we use any kind of base, that can be used to remove this proton, and then acylation can be done at this site also. So यहाँ पे एक बड़ा प्रॉब्लम ये आया था, या this is the reason, you see, because of this reason people have chosen anhydrous ALC, Lewis acid condition, because acid condition, what happens, acid don't get interact, and they have solved the problem of interaction of hydroxyl group to form the acetylation at this place via the acidic condition. So यहाँ पे जो हमने प्रॉब्लम फेस किया था, then I have give some conditions to him so that we can get the product. And I am not exploring the main content here, because we control the position of acylation via some chemistry there. So rather than the acyl group going towards this one, it goes here. This is what we call regioselectivity or chemoselectivity. Regio, not chemoselectivity, we call. So we can control the chemoselectivity via the control of functional group going to the which position. So the condition which we have given via various reactions, he tried I think almost like 10-20 reactions, and then finally we found that yes, the 3-step compound synthesis can be done in 1 step only, and this is practically proved. If you want to see, I can share the PDF file without recording to you later on if you want to see that one. Not only this one, the anti-TB compounds such as pyrazinamide, then isoniazide, then nicotinamide. These are the TB compounds also I have synthesized in the one pot. This is what we call one pot synthesis. Not only this one, we have several molecules is being synthesized. 6 to 7 molecules are there. The amination reaction strategy, which nowadays you are writing the thesis, that strategy already we have applied for the target molecule synthesis. And this is comes from what? This is comes from the retrosynthesis. This is what I am trying to explain you. Rather than taking the example from other synthesis, why not use the our one? And this looks simple also. So anyway, this is about the retrosynthesis of paracetamol or synthesis of, yes, कुठं आहे फिनॉलच्या खाली एस एम. आता हे हे का ॲक्च्युअली ते मी लाईन दिली ना त्याच्यामुळे कन्फ्यूज होत असेल. ॲक्च्युअली देर इज नथिंग. दिस इज द स्टार्टिंग मटेरियल. म्हणजे जे स्टार्टिंग मटेरियल आपण लास्टला दिलं होतं ना ते सिंथेसिसमध्ये पहिल्यांदा येतं. रिव्हर्स कॉन्सेप्ट आहे. CSM means starting material. Some I think Aishwarya told you it is true. Starting material. Is it everything is clear now? Okay. So try. We will not stop it. हाँ जी. एक्चुअली अलग अलग कॉन्सेप्ट है. जब मल्टी स्टेप सिंथेसिस आता है पोर्शन, तब क्या होता है कि एक कंपाउंड का कन्वर्शन दूसरे कंपाउंड में करते हैं और जो प्रोसेस रहता है, अभी आपको मैं प्रोसेस बता देता हूँ कि एक रिएक्शन के लिए क्या क्या करना पड़ता है. सबसे पहले उसको हमको स्टार्टिंग मटेरियल लेना पड़ता है सेम इक्विवेलेंट में. उसके बाद उसको हम फ्लास्क में ऐड करेंगे विथ सॉल्वेंट. समटाइम लिगैंड यूज़ करते हैं, समटाइम कैटलिस्ट यूज़ करते हैं, हीट भी करते हैं, या कभी कभी फोटोन के अंदर रिएक्शन डाल देते हैं. तो ये सब करने के बाद फर्स्ट स्टेप में रिएक्शन जो होता है, जैसे फिनॉल का कन्वर्शन हमने नाइट्रेशन कर दिया, तो ये जो नाइट्रेशन कंपाउंड बनता है इसमें क्या होता है, अनवांटेड इनऑर्गेनिक मटेरियल बहुत रहता है. क्योंकि साइड रिएक्शन के इसमें क्या होता है, बहुत सारे साइड प्रोडक्ट जनरेट होते हैं. तो इसके लिए एक प्रोसेस है एक्सट्रैक्शन वाला. तो हम क्या करते हैं, इसको जो कंपाउंड बना है उसको पहले न्यूट्रलाइज करते हैं. फर्स्ट स्टेप इज दैट वी हैव टू न्यूट्रलाइज बिकॉज वी आर यूजिंग अ एसिडिक कंडीशन. सो द फ्लास्क कंटेन्स एसिड. तो उसको न्यूट्रल करने के लिए क्या करना पड़ता है, वी हैव टू ट्रीट विद द बेस. तो कौन से बेस यूज कर सकते हैं, आइदर यू कैन यूज दी NHCO3 और सोडियम कार्बोनेट और सोडियम हाइड्रोक्साइड ऑल्सो. तो 1 नॉर्मल या 2 नॉर्मल के सॉल्यूशन बना के रखते हैं और उसको क्या करते हैं, उसको डायरेक्टली इसमें ऐड करते हैं. इसको क्वेंचिंग बोलते हैं हम सिंथेसिस में, क्वेंचिंग, या उसको हाइड्रोलिसिस भी बोलते हैं. जैसे ग्रिग्नार्ड में क्या हुआ था, मेटल इंसर्शन के बाद जब अटैक करता है एसिड के ऊपर तो एसिडिक फंक्शनल ग्रुप बन जाता है, लेकिन जो इनऑर्गेनिक पोर्शन मैग्नीशियम रहता था उसको ब्रेक करने के लिए वाटर डालना पड़ता था. तो दैट इज व्हाट वी कॉल हाइड्रोलिसिस. तो हाइड्रोलिसिस करने से क्या होता है, पीएच मेंटेन करने से वी विल गेट द टू कंपोनेंट्स. आई कैन शो यू समवेयर हियर इन द स्पेस. तो जो दो कंपोनेंट आते हैं, एक रहता है हमारा इनऑर्गेनिक पोर्शन और एक रहता है ऑर्गेनिक कंपाउंड. लेकिन यहाँ पे प्रॉब्लम क्या होता है कि ऑर्गेनिक कंपाउंड वाटर में डिजॉल्व नहीं होते. तो ऑर्गेनिक कंपाउंड क्या किस में जाते हैं, सॉल्वेंट्स में जाते हैं, ऑर्गेनिक सॉल्वेंट में. और जो इनऑर्गेनिक पोर्शन है इसलिए वो वाटर में जाते हैं. तो उसमें क्या होता है, जैसे न्यूट्रलाइजेशन होगा यहाँ पे, तो सेकंड स्टेप में उसको क्या करते हैं कि वाटर डाल देते हैं. वी विल गेट एक्सटेंशन. जो फनेल आपको पता है, जो आपने यूज भी किया है, उसमें हम क्या करते थे, यहाँ पे नॉब भी रहता है. तो यहाँ पे वी विल मिक्स द बोथ लेयर्स. वन लेयर विल बी एक्वियस लेयर एंड अदर लेयर विल बी ऑर्गेनिक लेयर. तो इसका एक्सट्रैक्शन करते थे हम. तो ये एक्सट्रैक्शन जब करते थे तो इथाइल एसीटेट भी यूज करते थे. तो ये क्या होता था, जो वाटर लेयर है उसमें इनऑर्गेनिक पोर्शन चला जाता है, बट दैट इज स्टिल इन द विद द ऑर्गेनिक कंपोनेंट. तो इथाइल एसीटेट को क्या करते, इसको हम कैसे शेक करते थे. शेक करने के बाद क्या होता था, जो भी इनऑर्गेनिक कंपोनेंट के साथ कंपाउंड हमारा है, ऑर्गेनिक कंपाउंड, वो क्या किस में जाता था, ऑर्गेनिक सॉल्वेंट में. तो ये दो लेयर जब हम फ्लास्क में सेपरेट करते थे, यहाँ पे एक फ्लास्क में हमने ऑर्गेनिक लेयर लिया और दूसरे फ्लास्क में हमने एक्वियस लेयर लिया. तो यहाँ पे OH2O वाला, तो उसको फेंकते नहीं थे. तो इसको हमको 3 टाइम या 4 टाइम एक्सट्रैक्शन करना पड़ता है. वाई, बिकॉज दिस वाटर लेयर स्टिल माइट कंटेन दी योर कंपाउंड. तो फिर ये वाटर लेयर अगेन इसमें वापस जाएगा. देन अगेन वी पुट द सॉल्वेंट इथाइल एसीटेट. फिर और शेक करना है और सेपरेट करना है. शेक करने के बाद क्या होगा, ऑर्गेनिक में जो कंपोनेंट है वो इनऑर्गेनिक में, इनऑर्गेनिक वाला कंपोनेंट जहाँ पे कंपाउंड है वो ऑर्गेनिक में चला जाएगा. देन जो ऑर्गेनिक लेयर हमने यहाँ पे लिया था उसी में ये सेकंड वाला पोर्शन जाएगा. तो ये और बढ़ जाएगा. फिर वाटर तो उतना ही रहेगा, वी आर नॉट एडिंग वाटर, तो जो और वाटर जो यहाँ पे बचा है उसमें और इथाइल एसीटेट डालना है। ये डिपेंड होता है 100 मिलीग्राम के लिए 5 ml, 500 मिलीग्राम के लिए 10 ml या 20 ml, 1 ग्राम के लिए 50 ml, तो 50-50 ml के 3-3 बार एक्सट्रैक्शन करने पड़ते हैं। और उसके बाद हमको 2 लेयर मिलेंगे, एक लेयर इसका ऑर्गेनिक कंपाउंड का मिलेगा, कंपोनेंट का जो ज़्यादा रहता है, सपोज हमने 75 ml ये कलेक्ट किया है, और 25 ml का वाटर लेयर रहता है छोटा वाला। तो इसको क्या करते हैं, हाउ टू मेक श्योर वेदर द स्टिल आवर कंपाउंड इज आउट देयर और नॉट, तो इसका क्या करते थे, हम एक टीएलसी लेते थे यूजुअली। जो प्रैक्टिकली अगर आपका होता था ना प्रोजेक्ट, तो व्हाट वी डू, वी चेक अ टीएलसी एंड वी सी द ऑर्गेनिक लेयर का जो भी ये है, यहाँ पे हम डालते थे ऑर्गेनिक पोर्शन, और यहाँ पे जो प्रोडक्ट है, अगर प्रोडक्ट अवेलेबल है लैब में तो उसका भी। तो इसका जब हम टीएलसी रन करते हैं, अगर प्रोडक्ट का स्पॉट यहाँ पे अपीयर होता है, तो ये जो ऑर्गेनिक लेयर, जो एक्वियस लेयर का स्पॉट अगर यहाँ पे कुछ दिखा रहा है, ऐसे स्लाइड दिखाएगा, ज़्यादा नहीं दिखाएगा, तो उसका मतलब होता है स्लाइट अमाउंट इज स्टिल देयर। तो उसको क्या करना पड़ता था, उसको और एक बार ये के साथ करना है 25 ml का। तो ये कब तक करना पड़ता है, जब तक यहाँ पे वो स्पॉट फिनिश नहीं हो जाता है। फिर इसके बाद क्या करेंगे, रोटावेपर में डालेंगे, या इसको फिर हम हॉट ओवन में इसको सॉल्वेंट निकालने के बाद वी गेट द कंपाउंड। तो ये कंपाउंड भी क्या रहता है, इम्प्योर रहता है, नॉट प्योर। तो इसको क्या करते हैं फिर, कॉलम क्रोमेटोग्राफी, कॉलम क्रोमेटोग्राफी करके उसको हम प्यूरिफाई करते हैं, और जो प्योर पोर्शन आता है उस प्योर पोर्शन का एनएमआर लेना है हमको, या टीएलसी लेना है, क्योंकि उसमें अगर अब हमारे पास तो एनएमआर नहीं है, तो व्हाट वी डू, वी टेक अ टीएलसी ऑफ द फाइनल कंपाउंड इफ वी सी ओनली वन स्पॉट, मेजर वन, एंड सम स्लाइड स्पॉट मे बी अपीयर डाउन और अप आल्सो, डिपेंड ऑन द पोलरिटी ऑफ कंपाउंड। अगर ये मेजर दिख रहा है तो वी कैन गो अहेड। तो यूजुअली एडवांस सिंथेसिस में nobody will use the impure compound, every time they will go for the column chromatography, and that's what the tricky part is appeared here. So in each step after column chromatography, after one day you have to use lot of solvent there and you get the very pure compound, and that way you can check the weight, how much weight you get the after the column chromatography, and that weight has to be checked with the starting material weight in order to synthesize the chemical yield, उसका अलग फार्मूला भी है। तो इसमें क्या होता था कि ये जो 90% 80% बोलते हैं ना, 100% कन्वर्शन टीएलसी पे दिखाता है, लेकिन थ्रू द कॉलम क्रोमेटोग्राफी वी गेट समवॉट लेस कंपाउंड, क्योंकि कंपाउंड जब हम इंसर्ट भी करते हैं कॉलम में तभी भी कुछ लॉस हो सकता है, और जैसे हम उसको आइसोलेट करने के बाद भी रिएक्शन को ये रोटावेपर पे निकालने के बाद कुछ क्लास को भी चिपक जाएगा, तो उससे क्या होता है 10-5% यील्ड कम हो जाता है। तो जो यील्ड कन्वर्जन सिंथेसिस में 80% दिया था वो रिलायबल था। तो उसके बाद उसका एनएमआर चेक करेंगे, जो प्योर कंपोनेंट मिला है उसका एनएमआर देखेंगे, एनएमआर में अगर लग रहा है कि प्योर है तभी जाके सेकंड स्टेप करना है हमको। और जो मैंने फर्स्ट स्टेप के लिए अभी सब कुछ बोला ना, ये सॉल्वेंट का एक्सट्रैक्शन वो सब, वो सेकंड स्टेप में फॉलो होता है। हाइड्रोलिसिस होगा, फिर लिथियम एल्यूमिनियम हाइड्राइड बहुत ज़्यादा स्ट्रांग है तो कूलिंग कंडीशन में उसको ड्राई भी ये करना पड़ता है, वाटर एक एक ड्रॉप वाटर ऐड करके एक्सोथर्मिक रिएक्शन होता है, तो एक एक ड्रॉप वाटर डाल के उसको न्यूट्रलाइज करना पड़ता है। फिर अनहाइड्राइड भी अगर यूज करते हैं, लेविस एसिड या ऐसे कुछ क्लोराइड रिएजेंट भी रहते हैं, वो भी अगर स्टार्टिंग मटेरियल में हमने ज़्यादा यूज किया तो उसको भी निकालना पड़ता है। तो ये जो 3 स्टेप बोले तो क्या होता है कि each स्टेप में वी हैव टू गो थ्रू द होल प्रोसेस, but in one part you don't have to do the process of purification. Once we knows that the compound is generated via TLC, NH2 ग्रुप आया है, तो सेम पॉट में हम क्या कर रहे हैं, दूसरा रिएजेंट ऐड कर रहे हैं। तो इसमें क्या हो रहा है, जो भी प्रोसेस लग रहा है हमको सिंथेसिस के द्वारा, द होल प्रोसेस हैज नॉट टू बी रिपीटेड, तो वो प्रोसेस मिस हो गई वहाँ पे। तो 3 स्टेप में अगर हमको यहाँ पे 1000 ml सॉल्वेंट लग रहा है सपोज, तो यहाँ पे हम क्या कर रहे हैं, उसको एक ही स्टेप में कर रहे हैं, तो वो 100 ml में कवर हो जाएगा। सो व्हाट वी आर सेविंग 900 ml। दिस इज जस्ट द सॉल्वेंट। वी आर ऑल्सो डीलिंग विद द हीट, वो 3 स्टेप के लिए कितना हीट लगेगा। वी आर ऑल्सो डीलिंग विद द रिएजेंट्स यूज, अगर एक्सपेंसिव रिएजेंट रहते हैं तो बहुत ज़्यादा अमाउंट लगता है, बल्क सिंथेसिस में और ज़्यादा लगता है। So if you calculate based on the 111 subtopics, it will be like very big synthesis or very expensive scheme will be there. अगर ये अभी भी अभी ये जो स्टेप दिए है ये इतना एक्सपेंसिव नहीं है। इफ वी गेट द पैरास्टामोल 1 रुपीज़ को अगर मिल रहा है फाइनली, पैकेट में आके। तो ये ऑलरेडी चीप ही मेथड है, लेकिन उसमें भी अभी क्या हो सकता है, अगर ये 1 रुपीज पे मिल रहा है, इफ वी गो थ्रू द आवर मेथड and if it is published, then what people will do, what the companies will do, they will do the patent. So I was preferring to do the patent also, लेकिन वो बाद में देख लेंगे हम। तो इसके लिए क्या है कि क्या होगा कि जो अगर 1 रुपीज में बन रहा है, देखो ये, तो थ्रू द 1 पॉट सिंथेसिस वो हमको 20 पैसे में बन जाएगा एक टैबलेट। अगर 20 पैसे में बन रहा है तो कंपनी का पर टैबलेट अगर 80 पैसा सेव हो रहा है उनका। ऑफ कोर्स अगर 1-2 पैसे या 5 पैसे भी सेव होते हैं ना कंपनी में बल्क अमाउंट में एक स्टेप के लिए, दे विल प्रिफर टू गो फॉर दैट वन। and this is what the unique character is for one pot synthesis is excellent tool for the synthesis of any molecules। लेकिन उसमें ट्रिक ये रहता है कि वी हैव टू कंट्रोल द फंक्शनैलिटीज वाया द कंट्रोल ऑफ द रिएक्शन कंडीशन, क्योंकि हम रिएक्शन कंडीशन के थ्रू ही सब कुछ कंट्रोल करते हैं। जो भी रिएक्शन परफॉर्म करते हैं, विदाउट एनी कंडीशन वी कैनॉट गेट द एक्सपेक्टेड प्रोडक्ट। एंड दिस इज व्हाट द वन पॉट सिंथेसिस इज द एक्सलेंट टूल, not only for paracetamol. This is just the example I have given here. There are several molecules in the literature they are preferring to synthesize, even the oseltamivir, the drug which is used for the antiviral. So that one have, I think, 11 step was published in 2016 somewhere, and somebody has prepared in 30 steps. So in Angiochem paper, yeah, this is one of the best journal in the world for the synthesis one. और उसमें एक पेपर पब्लिश हुआ है। तो उन लोगों ने क्या किया था वहाँ पे, अगर आपको बता दूं कि उन्होंने क्या किया कि 3 स्टेप, 1 स्टेप, 2 एंड 3 स्टेप का एक रिएक्शन डेवलप किया उन्होंने। जैसे हम, मेरा जो रिएक्शन था सिमिलर ही है, फिर दूसरे 3 स्टेप का एक रिएक्शन, तो ये 2 हो गए, और थर्ड 3 स्टेप का थर्ड रिएक्शन। तो इन्होंने 3 अलग अलग रिएक्शन को मिक्स करके 3 स्टेप डेवलप किए, और तीनों का, इन तीनों का मिलकर एक स्टेप कर दिया। तो कितने स्टेप हो गए, 3 3 3 एंड दिस 3। तो 12 स्टेप का रिएक्शन उन्होंने दिखाया कैसे, 1 पॉट में। देखो लोग कैसे अप्रोच करते हैं। और वो भी ओसेल्टामिविर। ओसेल्टामिविर इज वेरी वेरी डिफिकल्ट स्टीरियोकेमिस्ट्री का कंपाउंड है, शुगर मॉइटी भी रहता है उसमें, और बहुत सारे स्टीरियो सेंटर्स भी है, बट दे हैव कंट्रोल दिस वन, एंड दैट्स व्हाई प्रीवियसली दिस सेम कंपाउंड वाज सिंथेसाइज्ड बाय अदर कम्युनिटीज। मोर देन 30 स्टेप्स में भी बनाए हैं, 25 स्टेप्स में भी बनाए हैं। लेकिन ये जो पेपर आया एंग्यूकेम का, उसके बाद लोगों ने इसी वे से बनाना शुरू कर दिया, और इसीलिए जो भी हमारे पास अभी ओसेल्टामिविर टैबलेट आता है ना बल्क अमाउंट में, थ्रू दिस पेपर ओनली, उसका पेटेंट उन्होंने कर दिया बाद में, एंड दे कैन इजीली सिंथेसाइज इट विद इन फ्यू डेज। एक तो पीटर सी बर्गर नाम का जर्मनी का साइंटिस्ट है, उसने तो एक ऐसा किया, जैसे शुगर केमिस्ट्री में क्या होता है कि इन शुगर केमिस्ट्री वी हैव टू डू द ग्लाइकोसिलेशन, एक एक यूनिट को हम एक एक रिएक्शन करते हैं। उस बंदे ने तो पता है आपको, ही हैज डेवलप्ड ऑटोमेटेड सिंथेसिस का एक मशीन ही डेवलप किया है। अगर आप पीटर सी बर्गर नाम का आदमी गूगल पे सर्च करोगे, पीटर सी बर्गर, आपको एक मशीन दिखेगी उसके लैब में, और उस मशीन में उसने ऐसा डेवलपमेंट किया है, एक साइड से एक शुगर यूनिट वो इंजेक्ट करता है, फिर दूसरे साइड से दूसरा शुगर यूनिट इंजेक्ट करता है, और तीसरे साइड से रिएजेंट इंजेक्ट करता है, और वहाँ पे जो पोर्शन रहता है वो क्या करेगा मशीन, वो शुगर यूनिट को कपल कर देगा और उसके बाद आगे बढ़ाएगा। तो मेरा एक फ्रेंड था जोसेफ अब्राहम, ही वाज इन ताइवान, नाउ ही इज विथ हिज लैब। So 260, one of the largest synthetically used sugar, he has prepared 260 sugar units in within 2 to 3 days. So this is what the advancement of technology is being received in the worldwide. अगर 1-2 बनाते हो, डाइसैकेराइड बनाते हो, बहुत ज़्यादा टाइम जाता है, ट्राइसैकेराइड बनाओगे बहुत ज़्यादा टाइम जाता है। मुझे पता है पेंटासैकेराइड बनाने के लिए 4 साल, मैंने तो एक डाइसैकेराइड यूनिट बनाया था, आई हैव स्पेंड ऑलमोस्ट लाइक 2.4 ईयर। सिर्फ डाइसैकेराइड, जो हेपेरिन सल्फेट आपको पता है एंटीकोआगुलेंट बोल के यूज होता है हेपेरिन सल्फेट, उसका एक यूनिट मैंने बनाया था, डाइसैकेराइड यूनिट। इसमें एक ग्लूकोज यूनिट भी था, एंड अदर वी ऑल्सो हैव द आयोडो यूनिट विच इज एल फॉर्म शुगर, जो रेयर रहता है। इन दोनों का कॉम्बिनेशन मुझे प्रैक्टिकली करने के लिए 2.5 ईयर लगे थे, लेकिन बिकॉज ऑफ द पीटर सी बर्गर, ही वॉज अ एक्सलेंट कार्बोहाइड्रेट केमिस्ट, ही हैव द मशीन, और उस मशीन में 2-3 दिन में 260 शुगर यूनिट जोड़ जाते हैं। तो आप देख सकते हो कि क्लासिकल वे ऑफ सिंथेसिस नाउ इज इमर्ज टू द sophisticated instrument synthesis, and this is what the synthesis is very if it is easy if you understand, if you don't understand it's very tricky actually. So this was the answer of one pot synthesis. Actually one pot synthesis बहुत बहुत अच्छा डेवलपिंग टूल है. So anyway, आपको तो आंसर मिल गया ना. Alright. So looks like I have made the dirty of which is not thought, but anyway, we can just go ahead for 10 more minutes. So terms which are used in the retrosynthesis analysis are the terms where the reverse of synthesis. This is what we are studying so far, the disconnection approach. So the target molecule can be breaking down to the functional via the functional group interconversions, and that is what we call reverse of synthesis. Then disconnection is also there, where with the reverse operation of the reaction takes place. So it is imaginary, always it is imaginary. That's why the synthesis first comes in the mind and then it will flow in the flask. And this is what the people will do. So synthesis, they will think in the mind how we can make the units. Nowadays there are softwares also. You don't have even think it. The software, what we have to do, you just put the compound structure. The software will give you the target molecules, you know, the unit. You don't have to think it. Before, before I think looks like 25 years back, everybody has to think about the reactions and then go for the development. But nowadays we have such a good software. They will just put the feed of the structure, and they will the software will show you the disconnection everything. So you even don't have to think it, and software itself will give you the reaction condition for the joining of the small units. And this is what the disconnection is now is very improved in the current era. So TM is usually preferred in the various places. It is specifically used for the target molecule is to be synthesized. FGI, of course, functional group interconversion, and this is the way without functional group interconversion we cannot make any kind of synthesis. So in short, every time no need to explain the bigger molecules there, bigger text. So they have chosen the small one. Synthons, of course, everybody knows, we have also written it. The fragment which is resulting from the disconnection. So these are the synthons, imaginary compounds. Synthetic equivalence, of course, it is also the substrate where we will have the positively charged or negatively charged components there. So in retrosynthesis, of course, there are several more concepts are also there. So in specifically the target molecule was first we have to select it, and after selecting the target molecules, we have to break the bonds so that we can disconnect it in such a way that we can get the final target molecule via the smaller units. So this is what appears as in the retrosynthetic analysis. Next is that we have to disconnect bond using a reliable chemistry. Without knowing the reaction, we cannot break the bonds. So after the disconnection, we have to make it repeatedly so that until we get the starting material. जब तक स्टार्टिंग मटेरियल हमारे हाथ में नहीं आता है तब तक उसको हम ब्रेक करना पड़ता है. कॉम्प्रोमाइज नहीं कर सकते हैं. अगर आपने किसी का शुरू किया है तो वी मस्ट हाउ टू सिंथेसिस फिनिश इट, क्योंकि अगर एक वे से नहीं बन रहा है सेकंड वे से करना पड़ता है, सेकंड वे से नहीं बन रहा है थर्ड वे से करना पड़ता है. आई नो वन गर्ल फ्रॉम जर्मनी, she was trying very hard to synthesize the final molecule, and after 24 steps she failed in 25th reaction, and 25th reaction was the last one he want to synthesize it. And for only one reaction I think she spent 2 to 3 years for the optimization of the condition, reaction condition where she want to get the target one. And that's what the synthesis looks very difficult. Sometimes if you stuck somewhere it's difficult, so but you cannot compromise it. You must have to go for the finalization. There are thousands of compound in IITs also are left there because of the final molecule is not synthesized, but there are several intermediates has been synthesized in the several IIT laboratories. Now if you check with the IIT laboratories, if you ask the professor, they will say I have 20 molecules, I have 30 molecules, which is not finalized in the final step. So this is what we have to cannot compromise it. So at least one novel disconnection should be there. You cannot use the chemistry which is, of course we can use the reliable chemistry, but the chemistry which is being developed by the other person, and if you are just copying it, nobody will say it is novel. So we have to see the reaction, at least one should be new, that nobody has done that way with the synthesis. So we have to evaluate the pathways and also make the route very attractive. If you don't make the attractive route, nobody will go to hit it. So it should be the relatively available and inexpensive. If you don't use the inexpensive, then the target molecule will be very expensive, and that's why inexpensive starting materials available should be used. So efficient भी होना चाहिए. Okay, so this is I think enough today's session. So later on we will take continue. If anyone having questions.